This is problem 744 in Smith Van Ness, 8th edition. So in this problem, we've got a pump that's operating adiabatically, and the fluid is liquid water. Given a number of conditions, we're going to look at the first condition. We've got T1 and P1 entering. We've got a mass flow rate of 20 kilograms per second. The discharge pressure is P2, which in this case is 2,000 kilopascals. We're also given a pump efficiency, eta. And then what we want to find is we want to find the outlet temperature and the power requirements of the pump. So another way of saying this is sizing the pump. When someone asks you to size a pump, they're basically asking you to calculate the power requirements. So P1, T1, 100 kilopascals, 298 or 25 degrees C up to P2. We've done problems similar to this before. There are two ways that we could approach this problem. One, and what we're going to do in this problem is we're going to use the equation of state information that's given to us. They gave us a value of beta. Another approach would be to use the steam tables or water property tables. And we could do this, but what you got to realize is that we're not dealing with saturated liquid. We're not dealing with a superheated vapor, of course. This water at these conditions is a subcooled liquid. And our steam tables simply do not have information about enthalpies, entropies, volumes, so on and so forth for subcooled liquids. And so we're kind of stuck. We're going to have to use the equation of state information that we have. Another thing to realize as you're doing problems like this is that the inlet conditions are fully specified. Remember, we haven't really used this a lot, but you'll use this a lot more in your second semester of thermo. But if we look at the degrees of freedom for the inlet and outlet, we've got one phase, liquid water. We've got one component, liquid water. And so we have 2 degrees of freedom. And so for state 1, the inlet of the pump, we have both pressure and temperature specified, so there are no degrees of freedom. For the outlet condition, we only have the outlet pressure specified. So we still have 1 degree of freedom for this problem. So the question is, well, how do we know what's going on at the outlet? And this is where we need to go back and we need to look at the problem statement and figure out exactly what is being said and what that really means. We actually do have information about the outlet that can help us solve this problem. We're told that this pump is operating adiabatically. So that means it's well insulated, or there's negligible heat loss, especially compared to the work that's being done on our fluid. We're also told that the pump has an efficiency of 75%. So what does that mean? Well, it's 75% efficient compared to a 100% efficient pump. A 100% efficient pump is what we would have if our pump were operating reversibly and adiabatically. So that's what we're going to use for our to get the information that we need to solve this problem. If you see the two words reversible and adiabatic next to each other in any kind of sentence for a thermodynamics problem, the first thing you should think about is that this process that's reversible and adiabatic has a delta S equal to 0, or it's isentropic. So what this means is our 100% efficient pump is operating reversibly and adiabatically, and it's isentropic. So if we have S1 here, which we do, we could look it up or we could calculate it. We know that S2 is equal to S1. And so what that means is that to solve this problem, what we're going to do is we're going to calculate work for the ideal case. Then we'll use the efficiency to calculate work for the real case. if we wanted to, we could also calculate the lost work and things like that, but your book doesn't ask you to do that. We're just going to calculate the work. And then from there, we'll calculate the temperature change and be able to solve the problem. So what we're going to do is we're going to start with this isentropic process. To do that, we just go back to chapter 6. Delta S is equal to 0. And so what we want to do is we want to figure out how we can use that. All right. And so if you go back to chapter 6, where we dealt with liquids and calculations of delta S, you can go to page 215 and look at equation 628. Or you could go, your book does this for you in chapter 7 on page 288. So this is the fundamental property relation that we have for liquids that are given by this particular equation of state where you're given a beta value. ds is equal to Cp over T dt minus beta times V times dP. So what we're going to do in doing this calculation is we're first going to solve for T2. All right. If you think about this, when we solve for the work, what are we actually solving for? I didn't write this down, but the work, I'll write this down right here. Work for the ideal case is equal to what? This is just the first law. That's going to be delta H for the ideal case, or for the isentropic case. All right, so work isentropic or work ideal is the same. They're the same thing. That's equal to delta H. So that's why what we're trying to do first, we're going to use this delta S is equal to 0 to solve for T2. That will enable us to calculate delta H for the isentropic process, which will give us W for the isentropic process, and then we'll divide by the efficiency to get the work for the real process. So it's a little, it might seem a little convoluted now, but hopefully as you get used to doing these problems, it'll make sense. So in this equation, what I've done here is I've just taken the fundamental property relation we had in chapter 6 or chapter 7, and then we integrated it. And so what we did when we did the integration here is we assumed that Cp is constant. Now, is Cp constant? Well, technically not. All right, and for especially for gases, we did some problems in chapter 6 where we assumed that Cp was not constant, and so you had to take the polynomial functional form of Cp, plug it into this equation, and do the calculation to account for the fact that Cp is not constant. But for liquids, Cp is more constant than it is for gases. So we can assume that Cp is constant. What about beta? Well, if you see, we assume that beta is constant as well. And remember, going back to chapter 3 and chapter 6, assuming beta is constant is a pretty good assumption, especially for subcooled liquids. What about volume? Is volume constant? Well, technically not, right? Because we actually do have an equation of state where volume is a function of temperature and pressure. But if you look at this problem, and if we were actually to check things at the end, we would see that the volume is not changing by much. And that's generally the case for subcooled liquids. And so what we're going to use is we're going to pretend, or I shouldn't say pretend, we're going to assume that, use our good engineering judgment, we're not pretending, we're using good engineering judgment to say that the volume is constant. Now, if you remember, I think it was back in either chapters 5 or 6, we had some problems where we were doing this, and we also used an average volume. And so we could do that here too. We could calculate the volume at the inlet, the molar volume, or specific volume at the inlet. We could also calculate the specific volume at the outlet, and then we could use an average. That would be something we could do, but if you did that, notice we don't know what T2 is. We don't know what T2 is, and so we don't know what conditions we would use to find the volume at the outlet. And so this would actually, if you were to do this, would have to be an iterative process where you guess a T2, look at the volume, do the calculation, run through everything, and then recalculate T2, and then it would be a long process. And what you'll find is that the volume is changing by so little, it really doesn't make that much of a difference. So what we're going to use is we're going to use the molar or specific volume of our inlet condition to solve for T2. So in this equation, remember where we're at. We're using delta S is equal to 0 to calculate T2. Once we know that, we can calculate delta H for the isentropic process, and then calculate work for the isentropic process, and then calculate work for the real process. So here's our equation, and we're setting delta S equal to 0. We get C sub P data from table C3. All right, table C1 is for gases, for ideal gases. Table C3 is for liquids. And so in the table is given to us, water is given to us, the heat capacity is 9.069 times R. This is a heat capacity at 298, which thankfully is the temperature that we're at. And so we can get this C sub P value either in mole terms or on a mass basis. What about for the volume or specific volume? Here's where, again, we use some engineering judgment. All right, our inlet condition is 25 degrees C and 100 kilopascals. So 100 kilopascals is pretty close to just barely below atmospheric pressure. We're at 25 degrees C. What is the saturation pressure at 25 degrees C? It's quite a bit lower, right? If you look on table E1 for the saturation pressure at 25 degrees C, let me go ahead and look that value up. So 25 degrees C, saturation pressure is only 3.166 kilopascals. Right? So are we okay using a specific volume at 25 degrees C, specific volume of a saturated liquid at 25 degrees C, even though our pressure is 100 kilopascals and not 3 kilopascals? Well, again, in this case, I think we are. And the way you can think about this is how does volume depend on pressure? If you think back to chapter 3, if you look back on page 76, you'll see equation 3.4 where you have the isothermal compressibility. Remember, that was given to us as kappa. Kappa was defined as minus 1 over V times dV dP at constant temperature. Were we given a value of kappa? So kappa tells us how volume changes with pressure. So in this problem, were we given a value of kappa? If you look at the problem statement, we were not given a value of kappa. So that must mean that kappa is very, very small. All right, and so if kappa is very, very small, that means that volume basically has no dependence on pressure. Volume is primarily a function of temperature. And even then, volume is a pretty small function of temperature because we look at the value of beta. Beta is pretty small. That's a pretty small number that we're going to multiply through by a temperature or a delta T whenever we see it. So kappa in this problem is essentially 0. So that means that the molar volume or specific volume of water is not a function of pressure, and so we can just go to temperature at 298 or 25 degrees C. We can look up that value of the volume and use that in our calculations. So that's what we do. We take this equation, we integrated the fundamental property relation using those assumptions. We set delta S equal to 0. We solve for T2, and this is what we get. Solving for T2, we get a temperature of 298.185 degrees Kelvin. As you can see, that's barely an increase above our T1, which was 298.15. So we've got a temperature increase of 0.035 Kelvin. And the other thing to remember, we're still dealing with the isentropic process, right? I didn't put this in here because I don't like having subscripts that are super long when I'm doing calculations. But this, we're still dealing with the isentropic process. This is not the actual temperature change for our real process. Because remember, what are we trying to do? We're just trying to calculate delta S. Well, we use the delta S equals 0 for the isentropic process, so we can calculate T2. Then we can calculate delta H for the isentropic process, then work, and then work for the real process. So to calculate the work for the isentropic process, we use the first law, which just says that delta H for isentropic is equal to work for isentropic. And we go to the equation, and this again is an equation that we've used before. This is equation either 627 in your textbook in chapter 6 or equation 725 on page 288 in your textbook. And we're going to integrate this equation to get our delta H for the isentropic process. And so we do the same thing. We need to make some assumptions. Cp dt. All right, so we integrate this. It's going to be Cp delta T. Delta T is not very big, right? It's pretty small, but we're going to keep that term. All right, we can't just cross this term out because our equation of state is a function of temperature. What about this term? Well, we integrate dP, that's just delta P, right? So P2 minus P1. We're going to make the same assumption that we made before. Remember, volume is considered to be constant with respect to pressure. So volume, we're just going to use V1 that we looked up here. All right. What about this term, 1 minus beta times T? Well, beta is our volume expansivity term, which we're given. All right. What about T? T is changing, right? So what value of T do we use? Well, again, we're going to use, do we just cross this? Well, you can't just cross this out, right? Beta is a constant. Can we assume T is constant? Well, if you look at this, what's the difference between T2 and T1? It's really small, right? And what is a beta value anyway? The beta value is pretty small too. And we're taking the product of these two terms. So T is 298, give or take, what, 0.035, right? Beta is the value of beta, page up here, 257 times 10 to the minus 6. So 2.6 times 10 to the minus 4. So I take something that's 10 to the minus 4 times something that's 10 to the 2, I get 10 to the minus 2. I'm subtracting that for 1, so I've got, I'm still within a, this value is still going to be very close to 1. This term here is not making much of a difference, and so counting temperature as constant, again, is a reasonable assumption. So we just integrate this equation. And here I've got this written as the delta H for the isentropic process. I multiply by the molecular weight because I'm putting everything in molar terms. So delta H for the isentropic process is 34.3 joules per mole. Now I can calculate the work for the isentropic process. And to do that, when I do that, I'm going to take the delta H, I'm going to multiply by the mass flow rate, which remember was 20 kilograms per second. And then because I had things in a mole basis, I'm going to divide that by the molecular weight to get things into so that the mass units cancel out. and I get that the isentropic work required to do this pumping is 38.114 kilowatts. And that's a positive value, right? Because the pump is putting work into our system. So now, when we have a process where work is being required, if we want to calculate the real work, we take the theoretical or the isentropic work, the ideal work, and we divide. Remember, we divide by the efficiency. And so our real work is actually going to be more than the isentropic work, and that makes sense. And so our real work is about 50.82 kilowatts. Now what we need to do, remember we still haven't, your book asks you to calculate the outlet temperature. We calculated the outlet temperature for this theoretical process, the isentropic process, but we still haven't done the outlet temperature for the real process. So how do we do that? Well, we'll kind of work backwards from what we did earlier. We are going to take our work. What we'll do is we'll take our work for a real process and we'll just use the first law, which is equal to what? That'll be delta H for the real process, right? Use that, all right? Delta H for the real process is also given by this equation right here. And so that's what we'll do. Delta H for the real process is 45.737. In fact, we could have just taken this delta H up here and divided by 0.75 as well, since we didn't have any Q terms or anything else in our energy balance. So that's what we've got there. We then take this equation and we just write it for the real process, solve for T2, and this is what we get. T2, delta H real minus so on and so forth, we get 298.337 Kelvin. And as you can see, that's still a pretty small temperature change. And that's usually valid when we're dealing with smaller pressure drops in pumps. You really won't see very large temperature changes when you're pumping fluids until you get to really high, really high pressure drops across the pump. So another thing I want to go through is, what if we assume that the water was incompressible? That is, there's no equation of state. Volume is constant, so kappa is equal to 0, which we assumed up above, but also beta is equal to 0. No change in volume. How would we calculate for an incompressible fluid? How would we calculate the work that is required to pump from P1, T1 to P2 and T2? Well, we could do the problem in a very similar way to what we did above. So we know that for an isentropic process, delta S is equal to 0, right? And so what we could do is we could go directly to one of the 4 fundamental property relations we had back in chapter 6. This would be equation 6.9. So remember, if delta S is equal to 0, we want to calculate delta H isentropic, and then work isentropic, and then work for the real process. So here's our fundamental property relation. If delta S is equal to 0, ds is equal to 0, and so dH isentropic is equal to V times dP. That's a very simple integration. That's just delta H for the isentropic process is equal to work for the isentropic process. This is just our first law. And here's our integration, which is V times delta P. So we do that calculation, V times delta P, and I multiplied through by the mass flow rate just to get everything in kilowatts. And you can see we get 38.114 kilowatts. That should look familiar, right? That's exactly the same answer that we got to 3 decimal points where we included the beta term. We do the real work calculation where we divide through by the efficiency, and as you can expect, we get the same value for the actual work, for the real work. So this is a good illustration of the fact that for most subcooled liquids, you can easily, when the pressure drop is not that large, you can pretty easily assume that you have incompressible fluids, that is, volume is constant. Your equation for calculating the work required to do that is a very simple equation, and you will use this kind of equation probably, I can bet, several times when you're in your fluid mechanics course. If you ever assume incompressible fluids, I know in your heat transfer course, Chemie 333, there will be some applications where, for example, you're asked to calculate the size of a pump that's required to push fluid through a heat exchanger, and they will use an equation that's very similar to this to do that. Usually for complex flows that you'll find in heat exchangers, assuming an incompressible fluid is a very good assumption.